in the beta gamma complex is I'm going to erase this because I'm going to kind of use some of it here. So I'm going to erase and restart for beta gamma. Okay, so to start for beta gamma, I'm going to again draw my phospholipid bilayer. So now we're going to have, and if you remember correctly, for when you guys went over G protein coupled receptors, beta gamma, remember CCC, not AAA. So we're going to have an add-on here in the phospholipid bilayer. And so I'm going to label these for us. And so remember here we have the G protein coupled receptor, which is here. And then we have something called phospholipase C. So we have phospholipase C, which I just labeled it phospho C because I cannot fit that whole word in the small box I allowed. And then the last box, this protein, is going to be called protein kinase C. And I have abbreviated PKC. So if we remember, we have our ligand binding to our G protein coupled receptor, and it's going to allow for dissociation of our beta gamma complex. And that's going to bind to our phospholipase C. And just as in our beta gamma subunit or our G protein coupled receptor, it's going to, phospholipase C is going to pull from the phospholipid bilayer. So it's going to pull one of these phospholipids out, and it's going to use it. And it's going to break this phospholipid into IP3 and DAG. And it's starting to resemble a lot of this G protein coupled receptor from what you learned earlier. So what's going to happen is IP3 is going to bind to our endoplasmic reticulum, which I am drawing here, and I will label ER. Endoplasmic reticulum. And it's going to bind, and I'll draw it binding here. And so it's going to bind here, and it's going to allow the contents of the ER to be extruded out. And the contents that are in here is just calcium, just floating around in this endoplasmic reticulum. So once IP3 binds, it allows for the calcium to escape. And what's going to happen is it's going to find another protein in the cell, and that is called calmodulin. And I'm not going to write out the whole name, but I'll just call it CalM. And so calcium is going to bind to CalM, or calmodulin. And what's going to happen is calmodulin binded by calcium is going to cause protein kinase activation. So I'll write protein kinase activation. So this protein kinase activation is going to cause dephosphorylation, just like it did in the last drawing I drew out for us. So again, it causes dephosphorylation. And instead of closing channels, it's going to end up opening channels. So if you remember, we had closing potassium channels in the alpha subunit, but in the beta gamma complex, we're going to have opening of potassium channels. And that's going to cause is hyperpolarization, right? So we have hyperpolarization happening. And in turn, hyperpolarization, normally it causes an IPSP, right? An inhibitory reflex. So now that I just walked through what IP3 does, I'm going to again I'm going to walk you through what DAG does. So what DAG does, it's going to come over here and it's going to bind to PKC, or protein kinase C. So remember, this is DAG. And then what DAG is going to cause after binding to protein kinase C, remember, it causes protein kinase activation. And what protein kinase activation causes is depolarization. So you get dephosphorylation coming from IP3 and DAG. And then you again get opening of potassium channels, which causes hyperpolarization, which in turn leads to an IPSP. So let me walk you guys back through this again just to simplify it a little bit more. So for the first thing that's going to happen is we're going to have a neurotransmitter or a ligand binding to our G protein receptor. And normally it's going to be ACH or acetylcholine. So we have acetylcholine binding to our G protein receptor. That's going to cause the beta gamma subunit to dissociate from the alpha subunit. So the beta gamma subunit is going to go bind to phospholipase C. Phospholipase C is going to pull a phospholipid from the phospholipid bilayer, and it's going to turn it into IP3 and DAG. So we'll go over IP3 first. IP3 is going to be binding, or it's going to find an endoplasmic reticulum to bind to. Once the IP3 binds to an endoplasmic reticulum, it's going to allow the calcium that is trapped inside to be extruded out. So the calcium will leave the endoplasmic reticulum and it will find a protein called calmodulin. And what's going to happen is calcium is going to bind to calmodulin. Once this binding takes place, it's going to cause protein kinase activation, which leads to dephosphorylation of proteins and opens potassium channels. Once potassium channels are open, it allows for hyperpolarization, and that causes an IPSP. And going back to DAG, DAG will bind to protein kinase C. This will activate the protein kinase, and it will also cause dephosphorylation, which opens potassium channels, which then leads to hyperpolarization, which leads to an IPSP. So, in summary, beta gamma subunits normally lead to an IPSP, whereas alpha subunits of a muscarinic receptor lead to an EPSP.